Last talk of WITS, in which Ben is going to talk about type narrowing the hard way.
All right, thank you. Yep, so my student Hanwen and I have been thinking a lot about this problem of type narrowing, and we think that you should pay attention too. Type narrowing is a form of flow-sensitive typing. Okay, but to start us off, we all know TypeScript, and everyone knows that TypeScript is unsound, right? Yes? Yes. This might be a new unsoundness to you, though. Here's a function that says it's a recognizer for strings. Give me any x, and the type, x is string, is declaring that when this function returns true, the input was a string. When the function returns false, the input is not a string. So it's a form of type narrowing here. And this is all a lie. It's returning true always, no matter what the input is. And it turns out this type of lying is very, very common. Okay, so MyPy and PyWrite are just two of many systems that let you do the same thing. Any predicate that you write, it is not type checked to see whether or not it's a predicate. Flow is doing slightly better, but the type of type checking it does is limited to basically one-liners. So type narrowing in general is refining types in the type level based on tests that are happening at the term level in the program. So here's a very basic example of using type narrowing. The function add1 takes in any object, and it does a type test. If the object I'm looking at is a number, then I should be able to use it just like that and add 1 to it. So this should be totally type correct, and this one is safe and sound. In the other case, we're returning 0. And this type system feature, to me, is very fundamental to making gradual typing work at all, because you've got all this existing code written in JavaScript or Python or whichever. You don't want to have to rewrite it to use data type definitions and match statements. It's already got a logic in it, which has been tested and working. We should be able to type check that logic. And the other side of the story is, at least to me, one of the big value propositions of untyped code is it lets me talk to the outside world. I don't have types for everything in all the databases of the world, and to make these types is really painful. Rich Hickey has this great quote. He says, who's seen a Java project with 1,500 classes? And everybody in the room laughs, of course, because the types don't compose very well at the end of the day. So you have to make a new wrapper type every time two meet, and this just keeps going. So with untyped code, we make these ad hoc types all the time, and narrowing is a way of managing that, taking the ugly data from the outside world and then funneling that into something nicer for the type system to deal with. And you don't need to take my word for it that this is an interesting problem, because John Reynolds, back in 1968, he was looking at computing data type definitions from Lisp programs. And he noticed we should really be paying attention to what's happening in these conditional expressions, because they're talking about the types that the program is equipped to deal with here on out. Yeah, Reynolds, 1968. It's so long ago. OK, so we saw this first example. This is quite boring. This is just like Java. I check if something is an instance, and then I cast it. And we've gotten rid of a cast. We've saved one line. That's not very exciting. What else can we do with narrowing? Here's a bigger example solving the rainfall problem. And up at the top, I listed the language features that type narrowing needs to pay attention to make this work out. So we're taking in a list of weather reports, which is just sensor data. It's coming in the form of JSON objects. We're looking at each weather report object to see, is this first an object as opposed to an array or something else? And does the object have a field that points to rainfall? We could get bad data that's missing the field. If so, we ignore it. If we do have the field, then we can get the value out of the rainfall, check if that value is a number, and check if it's a sensible sensor reading. And if that's the case, let's add it to the list of readings that we found from the data. Sum up the total. At the end, we want the average rainfall, ignoring all the bad things. So there's very few types in this program, but it's enough that I claim this program should type check. As long as your checker knows about type narrowing, it should be able to make sense of this. We start with JSON, we refine it to object, we refine that further to number, and we're able to add up. Here's another example. We have a filter function. This is taking in a predicate. So the function here has a narrowing type. It takes in any t, and it decides if that thing of type t is actually of type type s. And then our other input to filter is a list of t, and we're returning a list of s at the end of the day. So we go through every element in the first list. If the predicate returns true, keep that element. Otherwise, ignore the element. And then finally, every element in our results should be an s. Okay, so we have a higher order use of narrowing in here. So Hanwen and I have been generalizing this into a litmus test suite for narrowing systems because we notice there's a lot of disagreement in the space with these type checkers doing different things and sometimes reporting type errors and sometimes saying everything's all clear. Starting off in the basic of is this a number, do something, otherwise something else, there's 3 dimensions that we think spread out from here. So one is dealing with compound structures. Where inside this piece of data are we doing a refinement? Second is dealing with other forms of control flow and really making the system compositional. And third is user-defined predicates, which is the topic I started off with. So we've put these together in what we call the if-t benchmark, because that's the first thing you notice with type narrowing, is if something has the type. And there's 3 parts to the benchmark. It's very inspired by B2T2, the benchmark for table types, where you have a core litmus test. Then we have some larger example programs, and the rainfall and filter are 2 of those examples. And the third part is a data sheet, so that you don't need to read the whole benchmark implementation to get a sense of what is the language doing for narrowing. So we'll go through these one by one. We're going to go fast over this part, though. Here's the core. There's those 4 main topics that I showed on the slide. That's the axes. And then there's several tests underneath each one. The example programs exercise several topics in an interesting way. So we saw filter and rainfall. Tree node I really like. This is a predicate. It's recursive. So taking in a structure and then checking whether everything inside of it means it actually is a tree node or not. Here's an example data sheet that we did for the sorbet type checker. So this is adding types to Ruby after the fact. And it's only the first few lines of the data sheet, but already you learn some interesting things. What is the name of the top type in sorbet? It has one. I never would have guessed it's called t.anything, but now we know. And the bottom type is called no return, and I think the dynamic type has its own interesting name. We should always just call it dynamic. But so we've run the benchmark now on 8 different languages. So we have going from left to right MyPy down to typed Clojure. I'll show you the results really quickly. Everyone agrees on basic narrowing, and then as we go further down the rows, we get more and more disagreement. Typed Racket and typed Clojure are both doing the best. See, typed Racket has an X here. Typed Clojure is better. That's no surprise since the creator of typed Clojure did his dissertation at IU under the creator of typed Racket. So it's better. And then it's a bit small on the side. The X's at the bottom row for predicate checked, those are capital X's as opposed to lowercase x's. So lowercase x's is where something failed. Uppercase X is where it failed unsoundly. And the unsound thing is what I'm really concerned about. OK, so the benchmark is online. Since this is WITS, I wanted to talk more about the implementation. What are these languages actually doing to get type narrowing? And there's 3 interesting points in this design space. Spoiler alert, almost all of the code is weighed on the easy way side. Everybody's doing the easy way. There's, oh man. Let's say there's 2 implementations each of the beautiful way and the hard way. And I really suspect that there's a nicer way to do narrowing than the hard way. It's a case where we have an ugly declarative spec for this type system feature. But I really don't know what to do about it, so maybe one of you can figure it out. Maybe Ning Ning can do it. All right, the beautiful way is set theoretic types, and the hard way is what I call occurrence typing. OK, and then type narrowing is our umbrella term for these. So easy way first. It could not be any easier than this. Take the type system that you have, take the type checker that you've implemented, look at the rule for typing if, and add one meta function to that rule. So before we start type checking the branches, we want to analyze the code that's right there for the conditional test. What we're going to get out of that is 2 refinements of the type environment. So there's a positive case and a negative case. So if our expression E0 says this is an int, in the positive case we know we have an int. In the negative case we know we have not int. Take that positive environment and use that to type check the first branch. And take the negative environment and use that to check the right branch. I'm going to show you a lot of code. This is what MyPy is doing for that. We're type checking an if statement, and it's exactly what we saw before. Where's the key function? There we go. Find is instance check. And I love the name here because it tells you a bit about the history. At first, this function was just looking for isInstance. And over time, it went deeper. It can deal with and. It can deal with or. Now it can deal with type guards, the predicates. But it still has the old name. Well, we get two maps, if and else. We use those to update our environment. We push that type map onto our context. And then we discard it when we go outside of the with statement. Okay, so everything else here is scaffolding to keep track of scopes for MyPy. The basic implementation is just what we're seeing here. And it's great that there's more work in this part of the type checker, but it affects very little else in the type checker. So you can tack it on afterwards, no problem. And that's probably why it's so compelling. TypeScript is doing the same thing. Here's the code in MyPy for analyze. And it's probably the first 0.5% of how big this function is. There's a lot of cases here for what kind of syntax are we doing an if statement on. OK, so we don't need to dig into this, but that's the analyze meta function. And you can find the link online. So there's two problems here with this easy way approach. Problem one, obviously, is that we're doing this backward analysis just based on syntax of the code. So whatever's sitting there in the if, we can learn from. But if there's any abstraction involved, it's going to be harder to learn from it. Problem two is that when we're doing narrowing, we'd really like to work with subsets of types. We'd like true semantic subtyping. But we don't have that. We're dealing with syntactic approximations. So for example, MyPy has a union type. You can take things out of a union. But intersections are not very precise. So this brings us to the beautiful way of doing type narrowing, which is to let's go full on with first-class support for set theoretic operators in our type system. So we extend the grammar of types to let us talk about union, intersection, negation, complement, all these things directly expressed, so it's exactly what you want. The intersection of any two types is well defined in this. No approximations where we're jumping up and down some class hierarchy. This is great, and it gets even better. So here's the declarative system for handling all of type narrowing. Castagna, Laurent, Nguyen, WITS'22. It shows up in the first section. I don't know if it's page 1 or page 2, but it's very early on. You see these 3 rules. We can handle all of narrowing just with this. So these rules on the right are the easiest ones to start with. If E has type tau, and that's what we're testing for, then we can check inside that context. Just E1 has type tau1. Great. If E does not have type tau, then we just check E2, and tau2 is what we're going to get. We know in both of these cases that one of the branches is unused. So we don't need to care about it for the full type checking result. And then the subtle part in making a whole if statement check out is finding a good split. You have an input type, divide that into 2 parts of a union, and then use those 2 parts to type check the positive and the negative branches. So there's a bit of backward reasoning going on here. You look at the code of what's happening inside the true branch, and then use that to find out what's the minimum type you need on the input, and then match that up with what's happening in the if statement. And then you can do this union elimination to split the 2 cases. And this was amazing to me when I saw this. So POPL 2024, type inference for the flatten function. Flatten is taking in a tree or a nested list. Okay, so we have list containing the list A and then the symbol B, list CD. We flatten that to just ABCD. And set theoretic types is able to infer a type for this. And it's a complicated type. This takes some time to read. Flatten has 2 cases. If you give it a tree of elements, you will get back a list. And every element of that list is guaranteed to not be a list. You have a sequence of elements, flat sequence. Also, if you call flatten with something that is not a list, which in our example is going to happen in the recursive case, what you get back is not a list. And here's my simple syntax for the type here. A nested thing is a recursive union. So it's either a list of nested things or it's not a list. And not a list starts with the universe of all types. A is any type. And just take away all the things that are lists. So problem solved. Well, in theory, not so much in practice. So type inference for flatten was 300 seconds.
No longer.
No longer, OK.
No, I mean, now it takes a few milliseconds.
Few milliseconds. Oh, that's fantastic. Maybe it is problem solved. I was going to. This example is also certainly out of date. OK, so this was a few years ago, trying to type check the numeric tower from typed Racket using set theoretic types. And it took over 15 minutes to check add. because there's many cases in the union. This is problem solved for sure. This is a different one, though. I think that this is still a challenge, the asymmetric predicate. So my function is called isEven, and it's checking two things. Do I have a number, and is that number even? X mod 2 is equal to 0. So the type here is saying implies X is number, and this is new for us. We were just talking about X is number before this. So implies says in the true case, I know something. In the false case, I learn nothing. And this is in my cheap syntactic world, the implies. So what's the ideal set theoretic type for this? We'd like to talk about the set of even numbers, so an infinite subset of the natural numbers. If we have an even input, we should get true. And if we have anything else, some type minus evens, we should get false. And I think there's no implementation that can handle this right now. But it's a great challenge for the future. This is unfair. I tried it on set theoretic types in Elixir, and it's just not a problem that that system is equipped to solve. Okay, so there's no singletons for integer. So it's no surprise that the type checker just loops forever here. It was also, this is an early prototype. The prototype's at least a year old. So now we come to the hardware, which can handle things like isEven. And we're back to syntactic approximations as a quick heads up. This is really ugly. This is our bad declarative system. We have 4 things coming out of the type checker. How are we doing on time, Nikki? 5 minutes left? OK. Yeah, I have too much code to show you up ahead. So what's coming out of typing for E? We're getting type tau. That's fine. We know types. We're getting 2 sets of propositions. So these are the type maps that we saw before. But now they're attached to every expression. And we're getting them in a bottom-up fashion as we type check. And then we also have this O. And O is really an issue with notation. When we talked about data structures before, like the rainfall field in an object, we need to know where inside the variable we're looking to refine the types. So O is keeping track of that. It's an index path. So there's many things not to like about this. There's complex output. Every time the type checker is looking at something, it needs to return basically this 4-tuple of results. So we're type checking false inside typed Racket here. And there's some syntax to make it a little bit nicer, but the return type is the singleton type for false, and there's all this other stuff that we have to tack on. So the entire type checker is more complicated to support occurrence typing, or to do type narrowing the hard way. We also have a complex environment. It's really a set of logical propositions. So we need to talk about normalization in here. We need to talk about implication between variables. Yep, it's also complicated in the code. But we are free of these ad hoc analyses. So instead of find is instance, where we're looking at the syntax of a test and trying to infer something from its structure, we just type check the test, and then we get back a prop set. And that's exactly what we want to continue type checking. So we extend our environment, and we're good to go. It's also compositional. So this program is extremely hard for an easy way type checker to handle. We've got a nested if. If x is a number and y is a string, then we can do x plus, because x is a number, and we can take string length on y. Now, you're not going to do nested if inside the MyPy style, right? Your function would just become forget it. You could maybe do 1 or 2 levels, but then you should go on. You should find better ways to spend your time. But then the killer for this is with occurrence typing, it's trivial now to detect a wrong predicate. So both of these are lying. F says it detects strings, but it's really looking for strings or numbers. And G says it's looking for numbers or Booleans, but it's not doing enough work. It's only looking for numbers. So both of these are very easy to check. Just the result that we currently have, P1, does that imply P2? Maybe I've got it backwards. OK, there is a fly in the ointment here. So the downside is the type errors are currently very hard to understand. Here are the 2 type errors we get for the 2 programs up above. And I left off the line number, so that does give you a good hint that you're looking at this line. But what is going on here? I expected this, huh? String, pipe, bang, string. And I got number, pipe, bang, number, in number, huh? Like, how could number, huh, x be wrong? There's work to do here. So this is the hard way occurrence typing. It's compositional, it's bottom-up, no ad hoc analysis, and it lets us check these custom predicates. But it's awfully complicated. So where do we go from here? I mean, there must be an easier way. And if I was talking to you 10 years ago, I would have been really optimistic that we can find it. I'm less optimistic now. But we have a benchmark now, so we can use that to guide design. So if you think you've got it solved, run it against the benchmark, and you'll have a quick litmus test to see if you're on track. We've been very interested in what we can do about the unsoundness that's currently in MyPy and TypeScript, short of overhauling the type checker from scratch. So Hanwen and I have been working on a property-based testing tool where we take a predicate and we turn that into a generator. And we're finding now positive and negative examples to test these predicates against and hopefully find some bugs. You know, we're optimistic we'll have something for ICFP, but time is running out. That's ongoing work. And then it's also worth thinking about, can we do narrowing beyond gradual types? So the Typed Rosette paper was a very nice application of this outside the gradual space. I mean, at the end of the day, to me, narrowing is about keeping track of side channels in the type system. The type system is taking control of things that the programmer can observe. Take these observations, reflect them up into the types. And I think that's something that almost all type languages should pay attention to. So with that, thank you.
Wondering why the I mean the design here seems very much type checker like, right? Like it is intended to be a kind of outgrowth of a type checker, to just be a very fancy type checker. But there's also sort of another sort of thread here where like you can design it like a static analysis tool, right? Mm-hmm. And maybe there it's a lot easier to handle like this complex control flow. Like rather than trying to do this all syntactically, you know, you just get a CFG out of your program and then you try to do like a data flow analysis in order to figure out whether your type predicates hold. How much variation is there among these tools and how they approach that?
Yeah, I think all these tools have it integrated with the type checker. It's like along the lines of what Mark was talking about with Scala. We want this stuff integrated in the core. That's a very interesting perspective, though. And if we've got a fully typed program, right, it would help the static analysis along. We'd have to see what the cost and time overhead would be, right? But it might be a clean way to do this. And then you're right, for TypeScript, we wouldn't have to overhaul.
Thank you for the great talk. This is a cynical statement, probably a wrong one, and I'm happy for you to correct me. But to some degree, maybe within those 10 years, we should have convinced more languages to have nice syntax for pattern matching so that we don't look at those terrible ifs.
Yeah.
Well, ifsies. But maybe there's something, well, perhaps there's something in terms of the expressivity that I'm missing. Maybe you do want these tests, maybe they are inherently expressive.
No, this sounds like a fantastic weekend project. Take the IFT benchmark and just, here's the better syntax. Now, language designers, go implement it. You could change the world.
You need it also with just pattern matching.
Okay.
Or if you have three variables in the match.
Those set theoretic types with pattern matching definitely makes sense. Great, cool, thanks.
So the unsoundness in MyPy, now that you noticed it, I don't understand why it's not easy to fix. I should be able to say, oh, if an annotation claims that something will teach me something in flow typing context, then call the flow typing function on the expression and check that what it says is a subset of a superset, whatever, of the claim.
Well, so the problem here is that return true, in this case, could be 50 lines of JavaScript or 50 lines of Python. And you need to know what observations did that code make about the variable in all paths.
But I would expect MyPy to say, in that case, no, I cannot check that this returns type X is string.
Yeah, and then people would just ignore MyPy.
Okay.
Yeah, so flow handles one-liners. It's very surprising to me. There's a ternary operator for if, okay? So flow will use that to check your type guards. But if you use the if statement, the multi-line version, it will not type check that.
So this is related to the fact that the check that you shown us is very non-compositional and checks only a small subset of the syntax, so that it does not even try to check those.
Yeah, and these are highly programmer-oriented languages. They want to be good for coding, not good for analysis.
Any other comments?
A question.
Yes.
Just is there an approach that, apart from ours, that can check when the check is done on application? Yeah, I mean, if and that there is an application of functions or nested applications.
Yeah,
So
we would have to check all these ugly languages, right?
yeah, that's why I asked you. I don't want to do it.
Yep. So let's run it offline. Yeah, let's
Yeah,
check and
okay.
see. I think some of them will go deep enough to get it.
Ben for the last talk.
Okay.